Okay, so I'll start the recording. Okay. Right. Hello, everybody, and welcome to the 2023 Data Science in PhD Data Science training. So a brief introduction about myself. I indeed defended my PhD in dynamical systems in Moscow and then lectured in different places, including in non-typically maths or applied places like Higher School of Economics in Moscow, and also recently was a data scientist in population health, where I also did some teaching, and now back in computer science. So what is my goal and what I would like to demonstrate to you? My goal is, after all those years, I've seen the beauty of maths. I've seen the scare that people have in maths sometimes, but I also have seen numerous cases where non-following very simple math rules had huge consequences. And the goal, at least for me, in this PhD training, will be to demonstrate all those important mathematical basics from a maybe slightly different application point of view. So we will run through simple measurements and see what each of them can bring into real life. And hopefully it will make all this quite useful for you, and you will see how to apply those basics better, or how to avoid the common pitfalls that arise in different unexpected places. So the brief plan of the sessions can be found here on this link, and I will share the slides later, so you can you can click on those links by yourselves. The plan that is currently online, and I think was distributed in the original email, is quite rough, because basically it follows what was when I last did this PhD training 2 years ago, I think, and lots happened since. So maybe not exactly in the first semester, so there are additions in the first semester as well, but in the second semester after Christmas, hopefully we'll be able to do more research that new geometric approach presented to you. Okay, so how I see the sessions, well, it's quite interesting. We have quite a few participants today. Thank you very much for coming. But online sessions is not my cup of tea, I should say, because I always feel a bit like talking to a mirror. And I will be very grateful for your participation. And actually, I quite expect a participation from you. And you're welcome. I will have some problems. I will ask some questions, and you're welcome to either answer them more or less live. You're welcome to turn your cameras if you can, or at least please use chatting function. So you're welcome to give your answers in a chat, because my firm understanding is that, well, practice makes wonders, even in very, 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 very simple things. And of course, if you have any questions, please lift your hand, or if I do not notice your hand for some strange reason, please don't hesitate just to ask your question, and I will be very grateful for that. Right, to start with, and to check that we can indeed see each other and communicate with each other, I've introduced myself. Can you please, in chat, type down a quick hi, and if you feel like that, a couple of words about you, or which department or which program or which university you're from, because there might be people from different places. Great. Thank you very much, Christian. That's a very good start. Hi, Flavia. Hi, Timothy. Oh, by the way, can you see the chat at the side of the screen, or is it only me who sees the chat? Great, so the chat is working, at least I can read it. Yes, thank you very much. Yeah, lots of University of Liverpool students. I wonder if there's anyone not from University of Liverpool. Oh, great. So it's very nice. Thank you for coming. Please keep testing the chat. And I think I'll move to the next slide. Okay, so this PhD training mostly devoted to data science. So the question is, what is data science? And there's the definition. Data science is a very interdisciplinary field that uses scientific methods to extract knowledge of patterns from the data. That's why different other names come into place, like pattern recognition, data mining, or some statisticians really think that data science is just a part of statistics. So contemporary data science, I think, has outgrown statistics quite significantly, and that's what we'll demonstrate later in the module. But we'll traditionally start with some kind of more traditional approach to data science, more statistical approach. So let's start with the basics. What is the problem with data? What do you think? What problems with data? Yeah, please.
It can be really messy.
Yes, absolutely. Can be very messy. Anything more concrete or anything in addition? Yes, messy data is absolutely spot on. And I even have a nice picture to demonstrate that.
Incomplete.
Yeah, exactly. It's incomplete.
Yeah, it could be informative, right?
Yeah, what kind of information we get from that pile? Absolutely. It's messy and it's also big, because every year data science is growing and growing and growing. The storage capacities are growing, which means that this pile is growing as well. Which means that trying to find anything in this pile is getting trickier. That's right. That's absolutely correct. With just the sheer growth of everything, what computational challenges can we also notice here? Well, what happens if we have just a larger file to analyze? Well, actually, various things. So starting with the data, yeah, because we can store anything, we can get it from anywhere, which means that it can come from untrusted sources. Then we have multiple repetitions. And again, how we can measure what is trusted, what is not trusted. That's the question of measurements, which actually what we start with our model, well, our training now. That's one of the huge problems. How to measure what is trusted, what is untrusted. How even to measure what is the same or not the same, similar or different. That was also mentioned at Vitaly's very introductory topological talk as well. But also, as mentioned, there are computational problems as well. Because the main goal after we've collected data is to find the patterns. And there's a known curse of dimensionality, which we will cover in more detail, but which also says that if dimensionality of our data grows, if we are trying to consider more variables, then a very unexpected and counterintuitive things might happen. So indeed, missing values is a problem. High computational cost is very much related to so-called combinatorial explosion, right? Because the more variables we have, if you start with a simple tree with some possibilities, as soon as we again add just one variable, at least binary, then for each tree branch, we should have 2 branches for a binary variable. And if our variable is larger than binary, then it's like a real explosion, which means that data processing is very, very, very expensive. So useful information, yes, that's a very, very good point, because with larger amount of information, we get higher false discovery rates. And it's hard to evaluate that. That's a huge problem. And for us as customers, it also means that we are not anonymized anymore. Somewhere there's always some information about us, and quite a lot of it. And unfortunately, the extracted information is most probably biased. And if this bias continues, it accumulates, and the consequences can be quite interesting. Well, the simple example, I don't know, is something like credit rating, which we all need to get mortgages or to get finances. Yes, and it's a very useful thing in our everyday life, but any tiny bias or anything like that, a tiny mistake, as we probably hear from time to time, can lead to huge consequences. And that is why it's very important to have the measurements in place to catch this bias early enough, or ideally to avoid this bias altogether. So there are many approaches to data analysis or data science. So, well, one of the question is, what's the difference between data analysis and data science? And the usual agreement that data analysis is something which is much less developed and does not try to discover new things from the data, just analyzes the existing patterns. But in reality, with this huge pile of the data, the most of the time is really spent on some kind of data cleaning, collecting, wrangling, transforming. And then we use statistics for simple underlying reasons of patterns. And machine learning ideally makes predictions from the data that we have. So that's all very good. Unless we try to rely on machine learning and machine predictions too much. So there's an example of automatic logic, which can be represented in the following dialogue. So statement 1, there's nothing better than eternal happiness. Statement 2, but a ham sandwich is better than nothing. Following machine logic, what follows? It follows that a ham sandwich is better than eternal happiness. Funny, isn't it? But that's quite typical. That's what we think about as robotic logic. And finally enough, in one of the previous PhD trainings, we had a sort of experiment. I asked participants to randomly search for at least one of the words. And the words that they suggested, most probably than not, represented a better alternative to a ham sandwich. For example, there were lots of abstract notions like indeed happiness, like love, like peace. But sometimes there was, I think, two suggestions. One was soup and another one quite similar. And for me, almost any of them were better than the initial ham sandwich. And for me, it sort of represented what can happen if we use machine learning, following the rules, but then introduce some kind of randomness. Because then quite often, strict machine logic does not look so nice to us humans, but with introduced randomness or random noise, in fact, we can evaluate it as being better. And that's again the problem of connection between something strictly logical and our human common sense. And in fact, for me, this connection is the problem of measurement. What kind of measurement we apply to the statements that we translate into machine language, and what kind of measurement we apply to the statement that we give, that we obtain from machines. So how we understand it. And I think ChatGPT actually uses that, our ability to like unusual things quite a lot. And there are more examples of similar use of patterns and measurements. For example, Swedish statistician Ole Hangström, in his book, gave the following example of a future super AI, which seems to be quite closer to the reality now in recent years than we ever thought about. So this super AI receives a very great task of increasing the overall happiness in the whole humanity. Can you suggest the innovative ways to easily solve this task? Yeah, that's good. Well, yeah, AI calculated the total happiness and noticed that with current definitions, the total happiness is negative. And then again, applying the strict mathematical logic and rules, notice that 0 is surely an increase from a negative number. And discovered an easy way to solve the task. Well, do you like it? I don't know. For me, again, that's an example of how incomplete definitions, or also incomplete or uncertain measuring tools, do not help. And quite often, especially nowadays, I hear that, well, look, we can't do everything, we can't measure everything, we just concentrate on the things that we can measure here and now. So let's have a look. There's another well-known example that can be represented in the following steps. So the first step is to measure everything that can be easily measured. The second step is to disregard everything that we can't easily measure. The third step is to totally disregard everything, in a sense that it's not only unmeasured, but we regard it as not being important. Well, what does it lead to? We can say that we stop noticing everything that can't be easily measured. And this is suicide. Why? Because in fact, those 4 steps are coming as a description of a well-known event or a well-known situation. Do you know what kind of situation is described here? It has a special name in economics or in politics. Well, if you studied in the UK school, then you should know about that. It's called McNamara fallacy. Any ideas why McNamara is famous? It's a question from history. If anyone can remember who McNamara is. A hint that he was an American politician, and especially he was famous in his organization or involvement in Vietnam War. So in that time and space, computers came into existence. So everything was mathematically modeled. And war as well was seen by McNamara as a mathematical model. And to simplify things, he made some suggestions about measurements or interactions within this mathematical model. So the main measurement tool was the enemy body counts. And again, quite a good logic behind it. By decreasing the enemy numbers, we just decrease their presence, which means that victory will be assured if the fewer enemy we have left. And also another a bit less known thing or assumption is that he also lowered admission standards to the military. And again, the logic was very similar and quite honorable, I'd say. The idea was all soldiers are equal, and with the right training and good equipment, all we need is just simple numbers. Well, we've all heard about the results, I think. And why I mentioned the lack of desire to measure things and the previous 4 steps, because actually there's an anecdotic case telling that when McNamara was just choosing his measurement tools, somebody mentioned to him the feelings of Vietnamese people, that those should be taken into account. And McNamara apparently even wrote down by a pencil in his notebook that variable to measure. But then he erased that writing with explanations that he does not know a good way to measure it, which means that this is not important. And unfortunately, sometimes it seems that in many regards, the approach is still the same. So we do what we can here and now, and just disregard everything that we cannot measure because it's not important. Well, the consequences can be interesting. So measurement tools. As mentioned, we are quite interested in machine learning, yeah, and just wanted to share this nice picture of machine learning in the eyes of Jan LeCun. So he stated that the reinforcement machine learning is like a cherry on a cake because we can just aid machine learning by giving some additional logical rules. We've seen what will happen if the machine just follows blindly the rules that we give it. Then there's a supervised learning, and it's very popular now, in fact, because well, labeling with data, I think a large, well, AlphaFold is one example, and ChatGPT, they in fact had huge help from human labelers. But still, the major bit and the main dream of humanity is to create the machines that will do proper unsupervised predictive learning. And that's like the whole essence of thinking. So every bit of them is important. And it's quite a sad thing to have a cake without any kind of icing or cream. And cherry on the top is a very nice thing as well. But still, we need to be able to have the answers to it. And that's why the module is mostly devoted to providing the essence or the skeleton on which all kind of machine learning and even statistical tools are based. So I will start with fundamentals of statistics and probability theory, starting with very, very simple real-life applications, hopefully demonstrating why more maths is needed in form of axioms and some more rigorous theorems. Then we'll progress to hypothesis and some bits of regression. And then, because we are trying to measure the things, then we'll deal with metrics on data, different kinds of data. And from purely statistical types of measure, we'll move to different, more geometric types of measurements, known as geometric invariants. We apply them to contemporary clustering methods, and also we'll see what will happen to the clustering if we take non-proper metrics. We'll briefly encounter dimensionality reduction of different kinds. And essentially the main goal will be to move to a dynamical geometric data analysis. Well, why dynamical? It's also, I think Vitaly prefers the continuous geometric data analysis, but I'm coming from dynamical systems. And for me, any kind of continuation, any kind of changes represents dynamics. And why dynamics is important, I suggest us to have a look at the following well-known spatial analysis problem. It's also called modifiable area unit problem. And that's what we encounter, in fact, in everyday life, year by year, when all of a sudden the political boundaries or some kind of healthcare boundaries are changed. So does it matter how we draw the boundaries? So look at those two regions. Except you can notice that 3 points are exactly the same. And suppose they demonstrate the very simple case of one illness amongst 3 clusters of 3 individuals in the population who spatially are represented by 3 dots. So they sort of live there or are present there. And the reason is the same, but the settings are different. So what are the disease rates in the first setting and in the second setting? So on both pictures, we have 2 regions. So in the first picture, the disease rate here at the upper part is 0, and in another part is a half, right? And in another region set, we also have 0, but in another region, instead of a half, we have 1. So twice as high. And that's much more worrying, isn't it? Which means that by just drawing a different boundary, we change the numerical outcome. So, well, the common approach after that is try to average things. So what will happen if we take the average in the first case and in the second case? So can you type in the chat, what will be the average illness rate for the whole region in the first setting with a curved boundary, and the average disease rate in the second setting with a straight boundary? What is the average disease rate for the whole region? Yeah, great. So 1/4, is it in which region? Is it in both? Yeah, exactly. So indeed, if you calculate the rate for the first one, it's 0.25 or 1/4. And if you take the second setting, yeah, and the second setting, the average will be 50%. So quite different indeed. And that demonstrates both the problem with different geometric things and the problem with averages themselves. And I'm often asked, especially in the last 3 years in population health, so, well, look, you see, it's a very synthetic mathematical situation. Can it happen in real life? And the answer is obviously yes. Mathematics just makes the things a bit clearer and easier to observe. Whilst if you want a real life example, well, sure. For example, there's a specific article or paper devoted to just that. They had a real life data and demonstrated how in real life data exactly the same spatial effect happens. And for me, again, that demonstrates how we need to see the dynamics. And sometimes that's a real life dynamics that we are concerned about, what will change in the world with time. But also there's an opposite situation. We need to be able to trace the change in the measurement tools if those are happening quicker than the changes in the real life. And that's why I think seeing these continuous changes and measurements is a very, very important thing indeed. Okay, but we started about averaging. Let's continue with that. So the next problem, what is the probability that a randomly chosen person has an above average number of legs? What do you think? Well, and a similar question, what is the average number of legs? So what do you think is the average number of legs in the whole population in the world, or at least in England? Well, any ideas? Can it be bigger than 3? Well, it's a stupid question, isn't it? But on the other hand, that's something that not many people really think about. So we can't have people with more than 2 legs. It's too rare even if it exists at all. I honestly don't know about those surviving cases at all. which means that it's either 2 legs, but we also unfortunately can have 0. But those cases are quite rare as well, which means that most probably it will be, yeah, it will be, I think, thank you very much. It's not even 90, it's 90%, but hopefully a bit higher, depending on which population you consider. And by the way, if you consider population of people, yes, if you consider population in a prosthetic ward in a hospital, then then this probability can be even 0, but usually this probability is indeed high. Yeah, absolutely, because I will, I think, review the answer. Arithmetic mean of legs, I even Googled it, it's close to 1.97, because most of us still have 2 legs, but there are cases with 1 leg or 0. Which means that when we choose a person at random, most probably it will be 2 legs. Which means that the probability is quite close to 1. The quiet probability is close to 0. That's a strange writing. I will need to reword it. Yes, so the probability to choose a person with exactly average number of legs is very, very small. And the similar question, can we find a person with a family, can we find a family with an average number of children? Can you guess what is the average number of children per family, say in the UK? Yeah, 2.57. I think it happened at some point, but indeed 1.9 is the close figure as well, and it indeed fluctuates dynamically. But the last time I checked, it was 1.7, but again, it's a very dynamic figure, so maybe it has changed. But anyway, choosing somebody with 2.57 or 1.9 or 1.7 number of children is a bit tricky, but probably is also possible depending on how we define a decimal child. So, well, we know all about problems with means, right? And we're very clever, which means that we will never fall into this trap being scientists, right? Well, I would wish so. Because there's also such thing as journal impact factor, which you might encounter pretty soon if you are doing any kind of PhD studies or trying to consider in research. So impact factor is defined by the formula in front of you. So it's basically the number of citations divided by the number of publications in the previous years. All good and nice and very sort of reasonable. Yeah. But there was also a case in Acta Crystallographica section A journal, when an article with quite a strange name, so quite a niche article, which also included the magic sentence that this paper could serve as a general citation, indeed received all the citations devoted to shelves, whatever it is. So the impact factor of the journal jumped very significantly, which means that for that particular event of time, it even had a much higher impact factor than Nature and Science. And that's despite the fact that the second most cited article had a much fewer number of citations. So as you see, the scientists also are not immune to that kind of measurements issues, even if their own mortgage or their own well-being or careers depend on it. And that also demonstrates the importance of having well-defined measurements and well-defined tools and well-defined background behind it. So I will just quickly demonstrate some notations that we'll usually use. Hopefully we are all very comfortable with that. So by this thick letter Z, we usually denote, do we know what? What is denoted by this thick letter Z? Great, it's indeed integers. Okay, but then the next question, what is an integer number? How do we define an integer number? Yeah, it's a long pause in answers, isn't it? Because I don't know if you've ever thought about it, but in fact, to define the most basic things is the hardest task of all. And in fact, we would need to start from the very beginning by defining natural numbers, then introducing integers from natural numbers. Then at some point, Peano axioms will, yes, a set like, yeah, but what do you mean by like? For example, minus a half, minus 2 divided by 2, 0 divided by 2, 1 divided by 2, 2 divided by 2, and so on. Is it similar? Is it like? So then we need to define what like is about, right? So that's a very good attempt. And well, I learned in school that we introduce natural numbers, which is just numbers that we use to count things. Then we add 0, add negatives, and build from there. But if you want it to be even more structured, then it's a very, very, very non-trivial question. Which means that in most basic things that we take for granted, those questions contain sometimes the hardest bits. So keep that in mind when trying to skim over very, very obvious events. But indeed, that is all integers. How about this thick letter R? What is this one? So what do we denote as a thick letter R? And if you can briefly describe what it is, yes, very good. That's real numbers. And how are real numbers different from integers? And again, it hides quite a wide, basic, but very important notion. It demonstrates the difference between countable and non-countable. Yeah, including half and so on. Not a negative number when squared. A negative number when squared. That will be not real because that's a very good attempt, Adam. So not a negative number when squared. Yeah, so you're trying to define it as not being not real. That's a good attempt, but then we will not be able to define imaginable numbers or complex numbers, because we start from something, then build up from there. And if we try to go the other way around, then we might have a problem, because then we'll have a gap That's union both rational and irrational numbers. That's indeed the most complete definition so far. So for that, we need to define rational numbers first, and rational numbers are just a ratio of integers. And irrational numbers, well, it's everything in between, which means that we do have something in between. And that's the main difference between integers, which we can count, and real numbers, which come from the, say, some interval on a line, which we cannot count no matter how we try. And discovery of those numbers at some point was a huge step forward in the science and in maths in particular. And there are some examples of those numbers. I think the first one, to my opinion, was pi, but maybe I'm wrong. There are many of those. Okay, so just a quick reminder that by curly brackets, we usually define a set or just a collection of some elements. And by this sign, we mean that the element belongs to the set. That's what we will use quite often. And a very similar sign, just without a line in the middle, will mean that we have not just one element, but several elements from a given set. Then just a sum sign, but hopefully you're very comfortable with it by now. And please focus on logic rather than on methods, because we will try to solve similar projects by different methods and try to compare them. Okay. So we are starting from some kind of descriptive statistics. We'll try to describe the data set that's in front of us. And then hopefully at some point, we'll jump to inferential statistics, even today. And you know, when you notice this jump, let me know, okay? Because it will be hidden. And actually, I really try to trace this kind of, how it's called, quantum leap. So quantum leap, when you're at the lecture, it's usually a sudden jump, which happens from the moment when you understand everything to the moment when you don't understand anything. So try to keep your eyes open, not to lose this leap from descriptive to inferential statistics. That's your task for today. I think we'll cover it today, but we'll see. Okay? Right. So what's the difference? The difference is that a descriptive statistics deals just with the data set at our hands, whilst the inferential statistics is when we try to do some kind of broader predictions for the general population or general problem. Okay, but we'll start with definitely descriptive statistics. And the mean, as we all know, is just defined by this formula. We just add everything together and divide by the number of experiments. And just to get us all in the mood, this problem, what's the average temperature in Liverpool? So I've cheated a bit. I've already found the average temperature by months, and then rewrote it in this set. And it turns out, to my surprise, or not so much surprise, that the average temperature in Liverpool is about 10 degrees. Well, it does feel like that, at least today, especially when compared with a very rainy weather yesterday. And again, just to remind that, especially later in life, we mostly deal with weighted average, which is basically the same kind of average, but with multiple appearances of one certain value, and then we can just give weight to that certain value and can compute the same kind of mean or arithmetic mean just using a quicker formula. So why do we need the formula at all? We all understand what a mean is. Well, because we hear quite often some bold statements using this kind of language. For example, suppose we see a corporation that reports that its policies are totally democratic because it has 50 stockholders, in total 600 votes, with an average of 12 votes per person. So how can we evaluate or critically appraise this statement? Do you think this statement is correct? Or maybe we can present some other considerations behind this claim? Not clear about the weights of each vote. Yes, there's well, usually that's also quite a good point, isn't it? Because if there's one person who is basically a dictator and decides everything with a single vote, then nothing else happens or nothing else matters. But suppose that we are in a sort of ideal world where indeed each vote has the same weight. But why do you think that it shouldn't be averaged? What's wrong with having an average? Well, average is just finding a number. Why shouldn't it be averaged? What's wrong with it? Okay, so assume each vote has exactly the same weight. Yeah. Then we can calculate the average. Yes, very good. It's indeed distribution because we indeed can calculate the average. There's not a problem with that. We just press one button and they find the average. So why not? But the question is, what can be hidden behind this average? Because indeed the distribution will be different. And well, the best way to demonstrate why and how can it be different is to give an example. So that's the simplest example I can come up with. Suppose that we know the distribution is indeed so skewed that 5 stockholders have 84 votes. Yeah. Yes. If 5 stockholders, the votes have the same weight, each of them, but they can be accumulated with different distributions. So in this particular example, indeed, the 5 important stockholders will accumulate the weight of the highest number of votes. And then obviously the control of the corporation will be theirs. And then indeed the average is still 12, but it doesn't matter much. And by the way, that's what, to my understanding, is demonstrated in the film about the Facebook. When he rewrote the formula of the calculation of the stock, so that all of a sudden his partner has lost his part. You're welcome to check that. Yeah. So average votes can represent real situation, but it can be different. And again, to demonstrate another possible way to calculate the averages is this problem. So suppose we have this distance time graph. Well, it can be not only speed, it can be also some kind of dynamic change of anything from population to stock market. And suppose we would like to find the average for whatever reason, well, to represent it somewhere. So from the picture, if we try to calculate it, we can find that on the first part, V1, the speed will be equal to 2, and V2 will be equal to 1/3. So the average speed, by using that formula, will be 7/6, right? But also, just by implementing using the formula, we can also calculate it like that. We can take total distance divided by total time, which in this case will be 3/4, and will not get 7/6. And my question is, what do you think is correct? And I think I will have a break now for 5 minutes. And you're welcome to think about this question. So think which answer is correct and how to justify it. Okay? So 5-minute break. Recording. So for this particular question about the average speed, what do you think? Which answer is correct? The first one or the second one? So can you please type down, what do you think? Is it the first answer that is correct or the second answer that is correct? Mm-hmm. Yeah, so we do have some variability of answers, which is very good, which means that people do think about it. Okay, so quite usual, the usual thing is try to, if you don't know which method is correct, try to find another method to check the results. So let's have a look again. We can see that the first speed was maintained for a different time when compared to the second speed, which means that in fact it will be a good idea to put weights behind each of those speeds. So in the previous attempt, we just added V1 and V2 together and divided by 2, which in fact means that we gave them the same weight. But if we understand that the time was different, that will demonstrate that the weight behind V1 and V2 should also be different. So for V2, the time that it was maintained was 3 times larger, which means that the weight probably should be 3 times larger. And then when we repeat the calculations with different weights, then the answer is indeed 3/4. So that is indeed the correct answer, because here the weight was important. So is it a real-life example? Well, yes, because averages, even such a simple measurement as average, can lead to different results, even on the similarly very same or similar data set. Especially if we do it blindly by using some kind of library functions or readily available tools, because very often things are measured as a time series, that is at regular intervals. For example, here, quite possibly we would have measured at 0, 2, and 4, and then the speed will be 0, 7, 3, and 3, and then just a simple blind brute force application by just implementing it into a tool and finding the average, then we'll get another answer, which again will unfortunately be wrong one. And that's why it's so important to understand what's going on, to have the formula, but also understanding what should we put inside this formula, how this tool, that it is just the formula, how this tool should be implemented for our particular setting. So the promised question, well, one attempt of this question is this one. So suppose we have, again, a mean, arithmetic mean, and suppose we know that it's positive. Then all values should also be positive. and there's the proof. For example, if we take 1 and 3, then the average is positive. For example, in the Liverpool, temperatures were all positive and the average was positive. So we've proven the claim. Well, I can't see all of you, but I can see that Vitaly starts smiling a bit, because this situation is quite often repeated in real life, when claims are attempted to be proven by examples. And yes, definitely not, because, well, we cannot prove the general case by giving examples, because there's always a possibility that a counterexample can also exist. Or in the case of Liverpool, having an average positive temperature unfortunately wouldn't mean that there will be no even snow. So, but what if we tried and tried and tried and tried and couldn't find any counterexamples, and we tried so hard for so long with so many computer power? Well, counterexamples disprove claims, but still, if we didn't find a counterexample, we cannot say anything. And that's why proving claims is so essential, because it's not enough to just try to exhaust everything, especially if we have the infinite number of cases, or just quite a large number of cases. We were able to disprove the claim, but proving a claim is a different beast. So suppose we know that all numbers are positive. Can we then prove that the mean is positive? And that's the task that I ask you to try at home. And to stimulate you just a bit, let's consider the problem: why prove obvious things at all? Well, why proving things? We know that they're correct. So what's the reason? Why wasting time on that? And I enjoy answering, well, because we can. Because that's one of the maybe not so many things that is left that gives us a real advantage when we think about AI. For example, large language models have been demonstrated to fail to make the consequence that is A is B, then B is A. So that kind of simple logical consequences, obvious for us, is still not mastered by large language models. And another question: what will happen if we just tell some rules to those language models? We all know that from each iteration, especially in ChatGPT, there's quite a team of people who revise its interactions with current customers, right? And from time to time, they introduce new rules to help the model to deal with those situations. So, is it enough to teach our machine learning tool a simple several rules of logic? And let's look at the counting ravens problem. So claim 1 is that all ravens are black. Suppose we saw many ravens and didn't see any white ravens yet, so we make this claim because we don't have any new information. From logical rules, by the rules of contraposition, from B following from A, we can say that not A follows from not B, and vice versa. So let's demonstrate it on this particular raven example. We had all ravens are black. So by contraposition rule, how can we reformulate it? We can reformulate it as non-black things are not ravens. In other words, if we see a non-black thing, then it's not a raven. And then, just following formal logic rules, we can come to a next real-life situation. If we see a next black raven, it sort of conforms to our previous beliefs that the ravens are black, right? But if we see a green apple, by contraposition rule, this surely should increase the chances of having no non-black thing, which is not a raven, and hence that should increase the chances that claim about ravens is also true. And that's again a very simple example of what can happen if blindly applying logical rules to words or to very obvious statements. And that's why it's so important to have our own proofs based on our own mathematical terms and logic. Well, there's a simple explanation that indeed we are mixing here, as we did before, finite and infinite things. So it's important not to just master some logical rules, but have other basic understanding behind it. For example, understand that in any particular setting, we need to deal with finite elements, and in another particular setting, the things can become infinite, and a different logic might apply to them. So these more interesting explanations can be found on the Wikipedia page, but I think we've got more than enough for today. Thank you very much for your attention and being present. And please remember to try yourself on that problem. So we know that all items are positive. Can we justify that the average is positive as well, just by using mathematical definitions? But that's all for today. Have you got any questions?
Let us first thank Olga for her presentation.